Where do you put a huge new airport in a jam-packed city like Hong Kong? The solution called for one of the biggest construction projects of the 20th century.
Just how crazy would you have to be to build one of the world's busiest airports here, right in the middle of the sea and in the heart of a typhoon zone?
It's a crazy idea that only became this due to some clever engineering know-how. Know-how that just wouldn't have been possible without a World War II bomber.
Oh, my word!
A Cold War spy bug.
Correct.
An 800-year-old water pump. A brass band. And a vintage racing car.
Oh dear.
Most people who pass through Hong Kong's Chek Lap Kok Airport have absolutely no idea what it took to build it.
Thank you. 15 years ago, I couldn't have done this. Well, not without a wetsuit.
The land for Hong Kong's new airport had to be created. It was one of the biggest reclamation projects of the 20th century. And it couldn't have been done without a 13th century water pump.
That land wasn't there. The roads, the runways, the buildings, the aircraft, none of it. It was all just sea.
But what led engineers to take on such an epic task? In the 1980s, Hong Kong was growing fast. The old airport, Kai Tak, was struggling to cope as passenger numbers rocketed. And Kai Tak's airport was famous for its perilous approach. Hot jet engine, that's one way to dry your washing. The city needed a new airport, but where?
There's just no good free space. The city is squeezed between the mountains on one side and the sea on the other. With space being such a rare and precious commodity, the residents of Hong Kong have long since learned to be very creative with how they use it. But for this project, the engineers came up with a plan that would make even these guys think twice.
Engineers looked out to sea. They set about blasting and levelling two islands off the coast of Hong Kong, Chek Lap Kok and Lam Chau. The plan was to join them and create one big island out of the blasted rock. Except the seabed between the islands was soft marine clay up to 20 meters deep, which isn't exactly the right stuff to build on. In fact, it'd be pretty stupid. If millions of tons of rock and sand were dumped on top, the airport could sink into the sea. The island needed a firm foundation, so they had to get rid of the clay. All of it. Engineers called in the world's largest fleet of dredger ships to suck it all up. The dredgers work like giant vacuum cleaners, and they rely on a connection that was invented in what is now Turkey 800 years ago. Back then, the ruler wanted to turn arid land above a river into lush green fields.
It sounds like the beginning of some fantastic ancient fairy tale. You know the kind of thing. Whoever manages this incredible feat gets the hand of the king's daughter in marriage, or is banished forever if they mess it up.
Undaunted, a genius inventor called Al-Jazari took on the challenge of moving water uphill. He created the world's first automated suction pump. Professor Al-Hassani is an expert in ancient technologies. And this pond is just what I need to see this pump in action. It's made from 21st century materials, but it works just like Al-Jazari's 13th century design.
So this is the resulting in... Well, not this exact one. Obviously, this is a replica. So what is it?
This is supposed to be a suction pump.
So this is a suction pump?
It is.
But hang on, they didn't have BMXs in...
1206.
1206,
yes.
They didn't have BMX bikes. So what's that here to represent in this?
This actually represents the water wheel that was driven by a river.
So the same river that supplied the water that was going to be pumped uphill to distribute to towns and villages actually supplied the power to do that.
Exactly.
And I'm guessing that has to be pedalled by somebody, and I'm guessing you're not doing that, Professor.
Oh, no, thanks very much.
OK, I'll do that.
The last thing I was expecting this morning was a workout. So, this piston is the heart of the machine. Just like a syringe, it sucks in water through a pipe from the pond, then drives it out through the chamber and up the outlet hose at the top. The flap valves mean the water can only go in one direction, upwards. And if you can suck up water, you can suck up mud.
You'll see that now it's clear water coming out and being pumped. But as we disturb the soil in the riverbed, then the sediments will go up with the water, and hence we have the beginning of dredging.
All Al-Jazari wanted to do was water some fields. But his pump made an airport in the sea possible.
I never did find out whether he won the hand of the king's daughter. I think I just made that bit up.
What was good for Al-Jazari in the 13th century was good for Hong Kong in the late 20th.
Just as Al-Jazari's pump sucks up water, the dredging team at Chek Lap Kok sucked up sludge from the seabed. Only they did it a bit faster. 10 tons a second for 2 years. You need a lot of bicycles for that.
And over those 2 years, the dredgers hoovered up enough mud to fill 28,000 Olympic swimming pools. The clay was too spongy for landfill, so the sludge had to be dumped out at sea. With all the mud sucked up, engineers had a stable base on which to build. And by 1995, the island for Hong Kong's new airport was complete. Building Hong Kong International Airport in the South China Sea solved the problem of space, but an airport at sea would expose aircraft to some dangerous weather. Hong Kong International Airport sits in the pathway of deadly typhoons. But meteorologists can easily see a typhoon hundreds of kilometers wide as it races in. It was, in fact, an invisible threat to planes that airport designers really worried about.
There is another kind of weather that can ambush unwary pilots, and it can be lethal for planes precisely because it is less predictable. It's wind shear.
Wind shear is any localized change in wind speed, and Hong Kong International Airport is located in a high-risk zone. Positioned between mountains and the ocean, normal wind patterns don't apply here. Rapid wind changes can affect the amount of lift on aircraft wings, causing planes to accelerate or stall catastrophically. Aircraft can literally fall out of the sky or be blown off course. In 1998, this Thai Airlines Boeing 777 attempted to land at Hong Kong's old airport. It's a smooth descent until the plane is blown off course just seconds before touchdown, landing on just one set of wheels. Successfully this time. But wind shear can be fatal. In the last 60 years, over 1,400 people have died in accidents caused by this invisible threat. Fortunately, planes in Hong Kong are protected from wind shear. And incredibly, all because of a connection to a brass band. A scientist called Christophorus Boyce-Ballot asked a brass band to help him test Christian Doppler's revolutionary theory that you can detect if something is moving towards you or away from you by measuring a change in frequency.
It was over 150 years ago that players, perhaps like these, were used to demonstrate a scientific principle that we take for granted nowadays, but that back then had to be explained and demonstrated and proven. It was 1845, and what the scientists did was put horn players on a train, because we have to get the horn players moving very quickly towards us and then away from us for this to work.
150 years ago, of course, scientists didn't have health and safety forms to fill in. Now there's no way I was going to be allowed to risk these young people to prove a theory. Luckily, we've got other things in the modern world that'll do the job. It doesn't play a tune, but it does make noise, and it moves fast. Now listen carefully to the sound of the engine.
As it gets closer and then further away, the noise it makes changes, but it doesn't just get louder and then quieter. It changes in pitch. It's called the Doppler effect.
It works like this. The plane produces sound waves. When it travels towards us, the waves bunch closer together, changing frequency and creating a higher pitched sound. As the plane flies away, the sound waves stretch out and the frequency and pitch change again. But what does the Doppler effect, or Doppler shift, have to do with detecting wind shear, those fast, potentially deadly, invisible currents of air? Well, using Doppler's principle, Hong Kong pioneered an advanced wind shear warning system. And the airport's first line of defence is 12 kilometres from the runway.
Chek Lap Kok is right the way over there on the horizon. You'll have to sort of trust me that it is, but it is. You can just see the towers. Over here, this is part of its wind shear and turbulence warning system. And yeah, it is distant, but because of the water, it's got clear line of sight.
This radar detects wind shear by looking for water droplets, usually rain. The radar waves bounce off the droplets and back to the tower. The airport can tell whether the rain is moving away from or towards the radar by measuring the change in frequency of the waves that bounce back, just like the sound of the plane changed as it flew past. Pilots can be alerted of big changes in frequency that can signal dangerous wind shear.
Even up this close, there's no sense that this mute, blank structure is watching, but it is, 24 hours a day. It's giving pilots flying into and out of Chek Lap Kok over there the comfort of knowing that someone has got an eye out for them, should Mother Nature decide to make things tricky.
But what if the water droplets are too small to detect, or the air's too dry? This Doppler radar is as good as blind. So Hong Kong International Airport went a stage further and pioneered a new way of using Doppler shift to detect the invisible threat.
Anything that moves and makes a noise can produce the Doppler shift. That's why you can hear it in police sirens, aeroplanes, or a band on a train. But it's not limited just to noise. You can also detect the shift in another waveform. Light.
And a special kind of light is the key to Hong Kong's other use of Doppler.
Right, a little experiment, I think. What I want to try and do is detect, see, wind shear. What I have here, obviously, is an enormous fan. Now, I know that that fan's on and creating a continuous stream current of air because I just switched it on. But what if there was no fan and you couldn't tell? How would you know that stream of air was there? Because, well, You can't see it. Air is invisible. And that's what presents the danger to aircraft. So I'm going to ask Steve over here to see if, using your helicopter, you can tell me whether that fan is on. Flying along, straight and level. Oh, no! Ah.
Fan was on then.
Yeah, it was definitely on. Can we have the fan off, please? Thank you. Now, I'm not going to pretend that what just happened there came as a surprise. Obviously, it didn't. But what if the pilot in our helicopter, oh dear, had been able to see that current of air, that wind shear? It wouldn't have come as a surprise. Things might have ended differently. Well, at Hong Kong, they do have a way of making the invisible visible. And it all relies on the fact that the air around us, although we think of it as being just empty and invisible, is full of millions of tiny particles. I don't mean the specks of dust you might see in a shaft of sunlight through a window. I mean microscopic particles. You could fit 100 of them across the width of a human hair. And if you can see those moving, then you can see air currents moving. Let me demonstrate. Turn on the fan. Right, so that's our current of air. That's the wind shear. I shall now introduce some particles to the air. Yeah, I mean, it's kind of working. It is kind of working, but I think we can do better by making an improvement. What I need to improve is the light. Obviously, there's some light in here, that's why you can see me, but I need some specific light that I can control. So let's fire up the fan, please, first of all. That's our wind shear, our moving current of air. Now, introduce, if you will, the microscopic particles. Well, the flower. I can't really make out anything in there, but if I shine the light from this torch, all of a sudden, where the light is reflected back off those moving particles, I can see it. If I turn it off, really nothing at all. With the light, you can see those particles moving. And that's how they do it at Hong Kong. Let's cut the fan, please. Obviously, they don't have people wandering around with big bags of flour to introduce particles into the air. They're already there. It's those microscopic particles, remember, that are all around us. And they don't use torches. They use lasers, but it's still light.
And it's from this unassuming box on the airport roof that the light comes. It's a laser called LiDAR. I'm taking a look inside with airport meteorologist Mr. Chan.
Wow, it's a sort of electric shed. What's this do then?
It's measuring winds, detecting wind shear over the airport.
It detects particles too small to be found using Doppler radar.
And is it doing that all the time? Does it do it sometimes?
Yeah, it's measuring continuously and detecting wind shear continuously over the airport.
So even now, as we're inside it, it's still keeping an eye on everything?
Yeah.
In fact, LiDAR is so accurate it can provide precise wind speeds up to 10 kilometers away. Hong Kong International Airport was the first to use Doppler this way, keeping aircraft safe from wind shear. Engineers could tick the box for getting planes in and out of Hong Kong's new airport safely, all thanks to a brass band.
All that remained was to build one of the world's largest enclosed spaces for the new terminal.
A breeze, except by now, the clock was ticking. Hong Kong was due to be handed back to China by the British government. The project had to be completed before the handover, giving the engineers just 3 years to build one of the world's biggest airports. But the fast-approaching deadline wasn't the engineers' only problem.
Here in Hong Kong, the designers were aiming to be very big. They wanted to create one of the biggest enclosed spaces in the world, and they wanted it to be light and airy.
A big space requires a big roof. At 700 meters wide and over a kilometer long, this was no ordinary roof. The airport architects insisted on a jaw-dropping design mirroring the rolling waves of the South China Sea. It was an engineer's nightmare. A roof this size would need lots of muscular columns to take its weight. But the architects didn't want heavyweight structures cluttering up their light, spacious terminal.
This is a huge space with almost nothing to stop passengers moving around freely. This is one of the pillars holding up the roof. The next one is all the way over there. And in the other direction, it's all the way over there. Those are huge spans.
So how do such a small number of thin columns support a big roof? The answer? Make the roof really light. Only trouble is, a light roof isn't usually strong. Funnily enough, making something light and strong is what plane designers have to do all the time.
For the solution, the designers looked to the heavens and found inspiration in a World War II bomber.
It's the Wellington, a twin-engine British bomber used for nighttime raids over Germany in the Second World War. The crucial thing about the airframe was its strength. British engineer Barnes Wallis had found a revolutionary way of making a frame light and strong. It looks more holes than metal, and the secret was in the way he arranged the material. It's not about the amount of metal you use, but how you use it. I've devised an experiment at my workshop to show how, with steel, less can be more.
OK, if we're ready, let's try and get it down, but let's get it between the bars.
I don't get just anyone to be my technical advisor. Martin Manning was the chief structural engineer at Hong Kong International Airport.
OK, can we get down there?
First, we're going to load up a standard I-beam used in buildings all over the world with 2.5 ton in weight, about the same as 2 family cars.
So, here we go.
As the chain slackens, the beam takes the full load.
You can see it bending now.
Yes, I can see the bend.
This 130-kilo beam is holding up. Just. What happens when we increase the weight to 3.5 tons?
Well, here we go.
So, let's slacken her off and have a look.
Take the load off the crane.
So when the chains start to go slack...
There she goes.
My word, that is not liking it at all.
Don't take it any further.
That's failed, isn't it? That's broken.
That is seriously broken.
That never even got near it.
The steel beam fails completely at 3.5 tons. You could give this beam more muscle by bulking up, but that would also make it heavier, and they didn't want that at Hong Kong. Amazingly, we can send the I-beam on a diet and still make it stronger. Think Wellington bomber. The answer lies in simple geometry.
So there are things you can do with just the same amount of material, the same weight, but organised in a different way, in a different shape, a different form.
Absolutely.
And that's what we're going to do next.
Yep.
We better tidy this up. That beam's really ruined.
Broken.
Spoiled.
We're in trouble now, I think.
Taking a cue from Barnes Wallis's Wellington design, I've reorganised the steel into a series of triangles. This lattice beam weighs almost 20 kilos less than the I-beam, yet it should be stronger, if the maths is right. The load is spread through the lattice, so it won't bend, or so Martin tells me.
And you think this will be stronger?
Yeah.
Just because of the shape, the arrangement?
I'm going to test Martin's confidence and load it with a much heavier weight.
Right, let's have the lot on. All of it.
We're loading up every slab we can find. That's 4.5 tons, a ton more than the I-beam could hold.
All the way back.
Remember, this lattice weighs less than the I-beam.
Settling.
It's down.
So if we watch it slacken off. Now at this point, the I-beam just folded. Look at that.
That's not moved at all. There we are.
No.
That's 4 tons of concrete and half ton of steel.
And that's now happily supporting, what, 4.5 tons? And it's not even... that's content.
Yeah, that's quite content. The other one easily failed at 3.5, so say it was safe at 2 3/4, say. So it's nearly twice the load.
And it couldn't be any clearer, could it?
So that shows how you arrange the steel makes a huge difference to the strength. Our lattice was composed of very strong triangles, just like the Wellington bomber. And a curved lattice of steel, also made of triangles, was exactly what the engineers needed to span the terminal roof in Hong Kong. Each 36-metre span could be bridged with just one huge but light lattice structure.
It supports itself without the need for hefty pillars getting in the way, leaving the space free for passengers like me to roam around.
But of course, the building is just the shell for the business of getting passengers onto planes.
Next, you need the stuff inside that makes it work, stuff like baggage handling. And the designers didn't want an ordinary system. They wanted to go one better than other airports.
Hong Kong International Airport carries 40 million or so bags a year and 3.5 million tons of cargo. Keeping track of it all is an immense task.
When you check in for a flight, you really want to be confident that your bags are going to come off the same aeroplane as you at the other end of your journey. And clearly, the designers here at Hong Kong Airport realise just how much having that confidence matters for passengers.
Airports around the globe rely on barcodes to identify a bag's destination and owner. But barcodes have a success rate of only 85%. That means Hong Kong could lose 6 million bags a year, not counting 500,000 tons of cargo. That'd be a long queue at the lost luggage counter. The designers wanted to do better, so engineers had to pioneer a more advanced system.
They wanted technology that allowed bags to be scanned at a distance and with greater accuracy. And they turned to a Cold War device for inspiration.
Moscow, 1952. A security sweep revealed a bug at the American embassy, hidden in a replica of the Great Seal presented by the Russians over 6 years before. It was a revolutionary passive device operating without any kind of internal power supply. Baffled, the CIA called it the Thing. But with no sign of a battery to power the bug, how was the signal being transmitted?
The answer provided the solution to creating Hong Kong's new baggage handling system.
When a Russian spy fired a specific radio frequency at the Thing, it powered up the microphone and broadcast the ambassador's secrets. And a similar passive device sorts luggage in Hong Kong. But how? Funnily enough, spybug technology is useful for sorting other things that don't know where they're going. Sheep. Here at a farm deep in the British countryside, farmer Richard Webber manages his flock with a passive device, just like the Thing.
So what have we got here?
You got an ear tag,
Yeah.
which is a visual tag, and a microchip.
And that is the microchip. That's the heart of the whole thing.
That's the microchip. When you excite that, it gives you the automatic number.
So that's the key to this entire system.
Yeah.
All right, and we're actually going to ID one of these lambs now.
Yep.
We're going to do it.
Yeah,
okay?
we are. We're going to put
So
in
once
a...
it's got that identity, that's its ID number for life. That's
Yeah.
who it is.
Well, we will link it through the handheld to the mother. So if you would like to hold the lamb.
Hold the creature, yes.
OK. And I'll put the tag in its ear.
You're going to have your ear pierced. Much
Tiger.
smart, but it's very fashionable.
Right. Now we're going to read the microchip.
Right.
And,
So that microchip is talking to the handheld, and that then
Yeah.
is going to feed the information.
and it's taking it, and now it's asking, what is it, a boy or a girl?
It's not labelled, is it?
Well, if you look between its legs,
excuse me. It's a boy.
a boy.
I believe.
OK, so we hit the ram on here,
Yeah.
and then it says, what breed is it?
Sheep.
Normally it's a Suffolk if it's got a black face.
Right.
Oh, so it's a Suffolk, and all done.
So from now on, whenever that machine ignites this thing and
Yeah.
sets this thing into action, it'll identify itself and it'll trigger all of that
Yeah.
information.
So the luggage, the sheep, has been tagged with a radio frequency identification chip, or RFID tag for short. But how does this tag help a farmer sort a flock of thousands? I've asked Richard to divide some sheep into 3 groups, according to their value, and we'll mix them all up and find out if we can sort the sheep back into their original pens.
What we've done is we've put a colour collar on to show you that these are the sheep that should go into that pen.
Right. So they're sorted into, we've got yellow collars.
Yeah, red collars on that pen and no collars at all in there. We'll mix them up and then we'll run them through the auto drafter, we call it, and it will read the chip and decide which pen it should go in.
So we're going to mix all of these 3 groups up, and
Yeah.
this device here is going to
Yeah.
sort them out again.
That's right.
All right, I like the confidence. You'll excuse me if I test it a little bit. I've just had a devious idea for
Yeah.
something I'd like to do before we mix them up.
Well, that's to be expected.
First, I have to catch a sheep, which actually isn't easy. I want to check this machine is reading the microchips and someone isn't herding the sheep by looking at the collars. The only thing to do is mix up some collars and see if the sheep are still sorted accurately. So where's a sheepdog when you need one?
You don't want to go in, Richard.
Well, they make a noise like a stick.
I don't make a noise like a stick. A stick doesn't make a noise, does it? Right, that's the 3 groups. They're only mixed, and now we're going to sort them.
Yep.
I'm guessing with this.
Yep. OK.
Here we go. It's a yellow collar.
Now, if it's a genuine yellow collar sheep, it should go straight on.
One door shut, and the other one opens, and it sent that one straight ahead.
Yep.
This is sort of hypnotic, watching it sort.
Red.
Reds, that's correct.
This sheep sorter sends a radio wave to activate the ear tag's passive microchip, exactly like the spy bug. The tag replies with its number, and the computer checks its records for the sheep's value, then decides where to send the sheep, regardless of collar.
And you don't have to do, you're not doing anything.
No, you could actually go and have some lunch if you wanted.
So the advantage of doing it this way is it can be done at a distance. You don't have
Yep.
to be there or read a barcode. It just, they talk to one another automatically and sort them.
That's right, and it is accurate. It's so accurate that I'll bet you 100 quid that your yellow collar and your red collar is in that pen. There will be one without a collar in that pen, and there will be one without a collar in that pen.
A farmer just bet me money. I'm not going to take that. All right, fair enough. If you're that confident, we'll see if it has worked.
OK.
OK, so we're looking for a red collar and a yellow collar in here. Oh,
Yeah.
I can see the yellow one already. That's the yellow collar. Yellow collar here. And the red one.
Despite me mixing up the collars, Richard's RFID sheep sorting system soon saw through my cheating.
So it's all about information and it's all about readability. And, well, it's a system very much like this, though without the lambs in it, obviously, that allows them to handle the baggage at Hong Kong International Airport without actually handling it.
Hong Kong was one of the first airports to replace barcodes with RFID tags to track bags, thanks to Soviet spies. The luggage can be sorted accurately at high speed. 40,000 every 24 hours getting to the right plane 97% of the time.
Well, my bag is safely on its way to my plane, and very shortly I shall be joining it. Just time, I think, for a coffee and perhaps some shopping.
In a terminal with so much space, there's no shortage of room for retail therapy. But the size of this building posed another problem for the airport engineers. Remember those typhoons? These severe tropical storms have their own internationally recognized scale of destruction. At the top of the scale, Category 5, wind speeds can escalate to 250 kilometers an hour. These typhoons wreak havoc in Hong Kong, sending everyone running for cover.
Hurricane-force winds also cause problems for big buildings with high, flat sides. Exactly like this one, then.
To protect Hong Kong's new airport from destruction, engineers looked to another type of transport and found the answer in a 1930s racing car. Engineers knew the solution had to be strong enough to keep the building together, but just how strong did it have to be?
Thinking about the kinds of pressures these buildings have to stand up to, and we could look at the numbers all day long, but how do they actually feel? What happens? Well, to find out about that, I've come to the one place where I can be in control of the weather. A wind tunnel. A really, really big wind tunnel.
I've asked engineer David Wayne to let me play in his expensive wind tunnel.
Dave, so what's the fastest wind this tunnel can generate?
130 kph, 80 mile per hour.
So that's about hurricane strength, isn't it?
It is, yes.
And you're prepared to fire it up and let me stand there. I just want to feel what that feels like.
Yeah, if you're quite happy to do that, then yes.
Why are you smiling like that? will it blow me over at that speed?
It is quite likely to, yes. Right. If you're not bracing yourself, if you're not expecting it, then yes, it will knock you over.
Right. Will it then blow me to the other end of the wind tunnel where I'll come out like chips?
No, hopefully not.
Good.
Once you're on the floor, then that's it. You shouldn't go any further.
Okay. Well, this is just about feeling that pressure that these buildings have to put up with. So, in the name of science, switch it on. I'll stand over here. All I want to do is just get a real physical feeling of the kind of forces in a typhoon. I mean, how windy is a typhoon? 130 kilometres, 80 mile an hour. I think it's breezy, but how windy is it, really? And why did they put a mattress strapped to the floor immediately behind me? Okay, that's breezy.
David signals the wind speeds already up to 40 kilometres an hour.
Oh, that's nippy. Oh. So this is at about
70 kilometres an hour. That's gale force strength.
Just feeling the pressure. I mean, I'm feeling that on me now. That's as a bloke, not a big bloke at that. If I was a whole building, imagine the pressure's on me just at this speed.
David cranks it up to 100 kilometres an hour. Probably as well that I don't wear a toupee. It's not long before we're hitting 112 kilometres an hour. 130 kilometres an hour, this wind tunnel's top speed. This is equivalent to a Category 1 typhoon. Just imagine a Category 5, almost double this speed. Well, I think I've made my point.
Yeah. Well, sometimes numbers, theories aren't enough. And you just got to experience something physically for yourself. And all I learnt there was wind, moving air can be very, very powerful stuff, even when you're just a small bloke. If I was the side of a huge building, the pressures would be incredible.
The walls were reinforced to cope with the immense loads. Unfortunately for the engineers, strong winds stress the roof in a different way.
Every aeroplane using this airport relies on one thing to get into the skies: lift. And one of the secrets to creating that lift lies in air moving quickly across a surface. That terminal roof is a very big surface. Add in some fast-moving air, and there's the potential for a very, very big problem.
Back at the wind tunnel, I'm going to find out what happens to a curved roof when it's hit by a typhoon-strength wind.
I have here a small building. Well, it's very small, but I have more to the point over here, a roof. And it's got a profile a bit like the one at Hong Kong. And I understand the theory is that because of this shape, it'll work like an aircraft wing, and that'll generate lift, and it'll be lifted up off the building. But I kind of need to feel that happening for myself. So I've got the roof, I've got the building, I've got the wind tunnel to make the wind going over the top. I feel an experiment coming on. I've got to get in a small building. Tricky. Okay. I'm in. I mean, it's basic, but it's home. Right, I need my roof now, please. And I can find out just how it feels. Right. Ah, yes, one important feature. This is quite an expensive facility we're in, so just in case it does lift the roof off, I'm chaining it in place so it can't fly through the expensive fans at the end of the wind tunnel. Right, one of those, all done. Okay.
Remember, this wind tunnel can reach wind speeds of a Category 1 typhoon, 130 kilometers an hour. Let's see if that's enough for this roof to fly.
Well, I think you can see how the wind curves its way over the roof, but as yet, that isn't resulting in any lift.
40 kilometers an hour and rising.
Now it's getting windier. My roof's still on. This whole wall is vibrating as the wind's hitting it face on. Ooh, something happened there. Some movement from the roof. I'm not doing any of this, it's just happening. Whoa, 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 whoa. All of a sudden, that's not me, that's my roof.
At just over 55 kilometers an hour, this roof takes off.
My building is in a terrible state. It's broken the chains. You can just feel the lift. It passes a critical point and then wallop! The roof just wants to take off. It feels like a wing. Well, the big bad wolf didn't get in, but what I could feel then was the two stresses facing a building in a strong wind. Because initially there's the wind just hitting the side of it there and it wants to just collapse the building that way. And then suddenly when the wind grew and grew and grew, there came a point when the roof was at peril. And it wasn't that it was just being blown that way, it was actually being lifted up. So that's two very distinct and separate stresses on a building. One, this way, collapsing the walls, and the other, lifting the roof off. That's a problem.
One way to hold a flyaway roof is to lock it down tight. But this would call for a beefy building, precisely what the architects didn't want. The airport engineers came up with a better idea, and the key was flexibility, thanks to a pioneering joint from a 1930s racing car.
There it is. That is a Silver Arrow, a 1930s Mercedes racing car. And it featured a revolutionary new form of suspension that Mercedes had been pioneering. Probably one of the things that helped it dominate the 1937 Grand Prix season. But no sooner had that suspension been pioneered than it cascaded down from racing cars like that to more ordinary, everyday cars, and you can still see it in use today. And there it is. It's a wishbone.
A wishbone is a triangle of strengthened steel. It only allows movement up and down, stopping the wheels from moving in any other direction. Back at my workshop, I've come up with a little demonstration to pit flexibility against stiffness.
There is an old fable about a sturdy oak tree being blown down in a storm and a tiny reed surviving it because it could bend with the wind. Well, I've devised a little illustration to prove how flexibility can be a greater defence than sturdiness, and that, of course, was the solution at Hong Kong International Airport. Here it is. This is, well, it's a car, obviously, not mine. What I've done is weld up the suspension. It's now solid, the link between the wheel and the car. There's no flexibility in there at all. That's enough words. I think we should just get on with this illustration. So lift it up, please. I'm going to move out of the way. OK, well, if everything's set, drop it. Oh, dear. Yeah, I think we can see what's happened here. It's the suspension where it's mounted to the car, because there was no flexibility, it was just solid and sturdy where we welded it up, has come through the bonnet. It's ruined. So that was the sturdy approach. Let's try flexibility now.
This car is flexible, but will it survive my stress test?
Now, this car has fully functioning suspension. I'm not trying to sell it to you, I'm just pointing out that this one has the flexibility that the other one didn't. So, let's go through the same process and have a look what a difference it makes. Take it up. I've just cleaned it as well. Right then, let's do it. Drop it. Well, it landed, definitely. Gravity did that bit. Question is, what kind of state is it in? Well, it's still flexible. Hang on. All of these are boding well, you see. The flexibility helped it weather the storm. But does it still work? And I guess, as the final proof, we should really see if it still works.
The car's wishbone inspired airport designers to join the roof and walls, making a flexible joint, allowing for movement during typhoons. But unlike the car's wishbone, airport engineers had to design for 3 movements, not just one. The roof lifts like an aircraft wing, so the wishbone allows for up and down movement. But wind blasting the glass walls translates into a sideways movement, so it also has a sliding mechanism. For even greater flexibility, a knuckle bearing links the wishbone to the sliding bar. A total of 1,300 wishbones allow the building to flex and move in typhoon winds, thanks to a vintage racing car.
So my flight's been called, and I'll board my plane knowing that my bag's been stowed safely and the plane will take off safely. Job done for the engineers of Hong Kong Airport.
Some 800 flights take off and land at Hong Kong International Airport every day, transporting over 48 million passengers each year. As planes take to the skies, very few travellers will have any idea of what an engineering achievement this airport really is. But it wouldn't have been possible without an 800-year-old water pump, a brass band, a Cold War spy bug, a World War II bomber, and a vintage racing car.